sunshine. I realize I am in sunshine. The skies are turning blue. Would you like to go to the top of sunshine?
All right, welcome to another video of Accept Truth with Joy. In this video, it's going to be a three-part series where I'm going to talk about what is a species. And so we're going to look at this in terms of, first, the science. What does science say about what species are? Then we're going to look at it in terms of the creation, and then we'll look at it in terms of the flood. So in science, when we say what is a species, first, the word species is Latin for kind, but what we really mean is that's the smallest independent evolutionary unit, that smallest unit that is a population of organisms that's evolving together. And these evolutionary forces of mutation, selection, gene flow, drift are operating on that unit. You know, even Darwin knew that it was hard to describe actually kind of like a written out sentence that would be perfect for all organisms in all time. And so he kind of said no one definition has yet satisfied all naturalists, yet every naturalist knows vaguely what he means when he speaks of a species. And there are lots of species on the planet. Okay, here I'm showing just the 30 orders of insects, but we've described more than 1 million species of insects, 1 million species. And there's probably another, 10 million right now living on Earth that are undescribed, that need to be described. And then there's another 1 million of other things that we've already described as well. So of the things that have described, half of them are insects. The other half are other things. But there's a lot of species out there, lots and lots of species. In fact, what's living on the Earth today represents less than 1% of what has lived on the Earth. So just think of that. There's easily been hundreds of millions of species that have lived on the planet. Now, when we try to then define what a species is, we use concepts. And so I'm going to talk about 3 concepts real briefly, but there are others as well. The biological species concept basically says that if a population of organisms, of individuals, are reproductively isolated from other populations, then they can be called a species. Ernst Mayr, one of the main proponents of this concept, said species are groups of actually or potentially interbreeding natural populations that are reproductively isolated from other such groups. So this concept actually works quite well for large sexually reproducing organisms. However, it doesn't work well for things that are extinct because they don't reproduce. It doesn't work well for things that are asexual, and it doesn't work well for things that you can't actually go out and somehow decipher whether or not one population is interbreeding with another population. The morphological species concept is based on differences and similarities. So this is advantageous because it's widely acceptable across all forms of life, including fossils. But the disadvantages is that the definitions are kind of arbitrary and authoritative. And then you have these issues of sometimes organisms don't have much morphology variation, like these roundworms. Sometimes organisms are good at hiding, like these frogs that are really good at being cryptic. Sometimes organisms have very different morphologies for the sexes. So males could look very different from females. So you might think those are 2 different species. And sometimes organisms are polymorphic. In other words, one species can have lots of different forms. These butterflies here, it turns out that's actually representing 2 species. So each column is a species with 7 different morphs, and they each have a morph that mimics the morph of the other species. So isn't that pretty, that's pretty amazing, right? And if you didn't know that, if you didn't have other ways of deciphering what that species is and you only used morphology, you'd probably get it wrong. Another concept that we use is the phylogenetic species concept. In this concept, you can use DNA data, morphology, behavior, anything else really, and you put that into a data set, and then you let the data set run through a statistical framework test or a way in which the data fights amongst itself until it comes up with the best evolutionary hypothesis of the relationships of the organisms that are presenting the data. And so you can do this to figure out what is one species from another species, because if a species is indeed this kind of isolated independent evolutionary unit, you would expect that their DNA, their morphology, their behavior, their other things are all shared, or at least a certain amount of that is shared among that group, right? And it's different from the other groups. So that's represented here in this tree, where you can see that the African savanna elephants all grouped together using these kinds of data, different from the African forest elephants and different from the Asian elephants. And when this species concept was applied, then we can now say that there are 3 species of elephants on planet Earth instead of just 2, which was previously thought. So this concept has also been very useful in the recent past. Now, it's important also, though, to know that the speed of evolution is important here as well, the rate at which species can be produced. Usually, this is very slow. We're talking hundreds of thousands of years for one species to split into 2, right? This takes a long, long, long time. However, it can be very fast, where you can have evolution within a few generations or even 1 generation. I want to show one example of this from the evolution of bacteria.
So what we ended up building was basically a petri dish, except that it's 2 feet by 4 feet. And the way we set it up is that there are 9 bands, and at the base of each of these bands, we put a normal petri dish thick agar with different amounts of antibiotic. On the outside, there's no antibiotic. Just in from that, there's barely more than the E. coli can survive. Inside of that, there's 10 times as much, 100 times, and then finally the middle band has 1,000 times as much antibiotic. And then across the top of it, pour some thin agar that bacteria can move around in. The background is black because there's ink in it, and the bacteria appear as white. First, you see they spread in the area where there's no antibiotic, up until the point they can no longer survive. Then a mutant appears on the right. It's resistant to the antibiotic, it spreads, until it starts to compete with other mutants around it. When these mutants hit the next boundary, they too have to pause and develop new mutations to make it into 10 times as much antibiotic. And then you see the different mutants repeat this at 100. And after about 11 days, they finally make it into 1,000 times as much antibiotic as the wild type can survive. And so we can see by this process of accumulating successive mutations that bacteria, which are normally sensitive to an antibiotic, can evolve resistance to extremely high concentrations in a short period of time.
So that's pretty amazing, right? I mean, within just a few generations, you can get these bacteria that have evolved and changed in response to their environment, right? Now, some people may say, well, but that's just bacteria. Well, there are other examples of very fast evolution creating different species as well. One mechanism that does this is what's called polyploidy, where you take the chromosomes and you copy those chromosomes into duplicate copies into the offspring. So you can go from one number of chromosomes into a higher number or even a lower number, but you can have these chromosomal numbers that are changing from one generation to the next. It's rare that this occurs, but it does happen, especially in plants. And this figure here is showing just an example of this, of these different species that they differ, not because really they differ in the fact that they had different amounts of chromosomes, different numbers of chromosomes. The genes essentially are pretty much the same, but when you have multiple copies of a gene, that sometimes can lead to longer petals or a little bit different colors and things like that. But then these flowers don't interbreed amongst themselves, right? And so polyploidy can, essentially in one generation, create a new species. 2 other examples of this come from Galapagos, from these species of birds. And in this case, what happened was this bird came, I think is this bird right here, came from a different island and somehow made its way onto this island and then hybridized with this species, Geospiza fortis. And then the offspring of here started interbreeding amongst themselves. Okay, so at first you have a little bit of close inbreeding. Usually that's not a good thing, but in this case, it turned out that they were able to get through those initial generations, creating an entirely new bird lineage, a new bird species. And again, this occurred within just a few generations. It didn't take long for this to happen. We saw this happen in real time. I think it was like 1981 when this occurred. And then this example from the stickleback fish these are researchers at the University of Bern found that this population of fish 150 years ago were introduced into this lake. So they didn't exist in this lake until 150 years ago. And then they've now seen that this species has split into two species. One lives in the main lake area and the other lives in the stream area. And so their ecologies are very different, and that's keeping the population separate. And so now you have two species that have evolved no more than 150 years ago. So this one was multiple generations, but not hundreds of millions, not hundreds of thousands of years or millions of years. But most evolution does happen, or does take a long, long time to happen. So the key concepts here, there are other ways in which you can define species. So again, nothing is perfect. Nothing's going to work for all species. So you kind of have to mix and match based on the system that you're working in on how you're going to decide what one species is and what one species isn't. Species in nature are not static too. This process of creating new species is a process, not a moment in time. So it's a film, it's a video, it's not a snapshot. It's not an individual picture. But if you put enough of these pictures together, which some investigators have been able to do using lots of different data, you can essentially turn all of those snapshots into a motion picture, and then we can see and determine what happened during the speciation process. It's difficult to do, but we're actually getting better and better at doing that and describing speciation. And speciation requires long amounts of time usually, but it can occur quickly. So that's the primer from the science side of what species are. Look to part 2 and part 3 for what does this have to do with creation and the flood.
Sunshine with me. The doors are open, the skies are too. Sunshine is coming in for me and you. Sunshine.